podcast. This podcast is on logarithms and their properties and also their graphs. So, learning targets for lesson 3.2. As the student, after the lesson, you will be able to understand the definition of a logarithm, transform an exponential expression into a logarithmic expression, and vice versa, logarithms back into exponential expressions. Understand basic logarithmic properties. Understand what is meant by a common logarithm and a natural logarithm. And then lastly, be able to graph logarithmic functions and transformations of logarithmic functions. All right, without further ado, let's go ahead and get started. All right, first of all, definition of a logarithm. Well, a logarithm simply is the inverse of an exponential equation. Inverse of an exponential. So if this is an exponential equation, there are certain steps that you can follow to convert any exponential into a logarithmic equation, or vice versa. So the first step, if you have this equation, b to the a power equals c, the first step is to identify the base. So if we're thinking the base of this exponential equation, the one thing you might think of is, okay, the base of the exponent. So that's the exponent, that's the base. So, and this is what it's equal to, that's the answer. So the base is b. So we identified the base, check, we've identified our base. Our base is b for this equation. The second step is to swoop, as in move, swoop the base to the other side of the equation, meaning only the base is what changes sides. So notice how we have a b, we have an a, and we have a c over here. So when we move this base over, only the base changes sides. So the b is no longer over here, a is left over here, and we've got both b and c over here. Well, our third step is to create the opposite type of equation from which you started. Well, you guys don't know what a log equation looks like, a logarithmic equation looks like, so it's kind of hard to know how to do that, but I'm going to tell you. So notice how a is on the left side of the equation. A is on the left side of the equation still, so it's still there. Notice it came down from the exponent because there is no base anymore. And what we write is, we write log, that's just a cursive L, nothing fancy. And we create a log equation of base b. And when we have a log, the base is a subscript. So it's log base b of c here. Log base b of c. And just some terminology, this b is still the base, just like this b was the base of an exponent. They're both bases. It's the base of an exponent, base of a log. And these are equivalent forms. Notice these are equivalent forms. So that's b, and this right here is called the argument. So log base b of c. C is the argument, b is the log base. Okay, so that is these are the basic steps to converting between exponential and logarithmic expressions. So we identify the base, we move the base to the other side, keeping other things on their respective sides of the equation. Notice how a stayed on the left side, c stayed on the right side, and then we just created the opposite type of equation from which we started. So we started with an exponential, so we needed to create a logarithmic. If we ever going in reverse, where we're starting with a logarithm and going to exponential, we would have to drop our log and create an exponential equation. Okay, so let's practice some of these. So practice converting between exponential and logarithmic and vice versa. All right, let's start with this one. So we've got 12 to the x power equals 17. So I brought in my steps from the last page, and here we go. So we start by identifying the base. So our base here is 12. So there's our base. We swoop the base to the other side of the equation. So 12 comes over here, and then we create the opposite type of equation from which we started, using this 12 as a base. So since I started an exponential, I'm going to have to create a logarithmic form. So x stays on the left, equals log. How do I know which one to use as my base, the 12 or the 17? Well, since the base was over here was 12, I know my log base has to be 12 as well. The base stays the base when you rewrite. So log base 12 of 17 equals x. And that is our answer for the rewritten version of this equation. This is the exponential. That is the logarithmic. All right, let's try this one. Notice it's in a different order this time. The exponential part's on the right side of the equation. So we still follow our steps. Identify the base. Well, the base of the exponent is 9, so that's our base. So that's going to swoop to the left side of the equation when we go to step 2. And again, we started in exponential form, so we're going to have to write it in logarithmic form. So we have log base 9 of 81 equals what's left on the right side? 2. Okay? So there's not that much to memorize here. Just identifying the base, swooping to the other side, and then creating a log of the same base that we started with. Since the base was 9 here, we got to create a log with a base of 9. 81 would start on the left side of the equation, so we know we got to put 9 with 81. And 2 start on the right side. Its 9 got taken away, so 2 stayed on the right side. All right, let's try some where we're working backwards, or starting with a log and going to exponential form. All right, so again, it works the same way. We can still follow the same rules. Identify the base. Base is 2. We swoop the base to the other side of the equation. Okay, we haven't run into this yet. What happens when we strip a log of its base? Well, a log cannot exist without its base. So think of it like the log dies, or the log disappears, gets dusted when you take away its base. So all that's left on the left side is 16. 2 is now over here on the right with the 4. And now we create the opposite type of equation from which we started. Well, we started with logs, now we're going to create an exponential. How do we know if it's 2 to the 4th or 4 to the 2? Well, we have to maintain our base. So it has to be 2 to the 4th because 2 is the base of the exponent 4, not 4 being the base of the exponent 2. So that's how we know it becomes 2 to the 4th power on the right side, just 16 on the left. 16 equals 2 to the 4th. All right, last one before I'm going to have you guys try some. Y equals log base 9 of x. All right, so identify our base. Our base is 9. Swoop the base to the other side, so that comes over here. Log dies. I'm left with just x on my right side. On the left side, I've got a 9 and a y, and I got to recreate an exponential of base that matches the base that it was. So it's 9 to the y power equals x. And those are our 4 answers to these types of problems. Follow the steps. All right, so I want you to pause the video now and try these next 2. All right, you've paused the video. Hopefully you tried these 2. Let's go ahead and work them out. So we want to identify the base. Base is 7. Swoop to the other side and recreate the opposite form. So we have log base 7 of 49 equals 2. Log base 7 of 49 equals 2. All right. Other problem, we have starting with a log, so we want to identify the base. It's m. M swoops to this side. Step 2. When we take away the base of a log, the log goes away, and we're left with y on the left side by itself. So y equals either 5 to the m or m to the 5th. We know, well, the base has to stay the same, so the only way that can happen, we got to maintain that base m. So the base is always the underneath part of the exponent. So y equals m to the 5th. And there we go. All right, so a few logarithmic conventions. So meaning like things that you need to be able to recognize with logarithms. Okay, what does it mean when you see a log with a missing base? So log without a base written here of 3. Well, I kind of think of it like this. If you just have an x written here, what's implied to be in front of the x? If you're thinking of 1, you're right. So there are certain conventions that we know. If there's nothing written, there's a 1 there. Well, that's not the same thing with logs. When there's nothing written, it's implied to be a log of base 10. So log with nothing written of 3, this is called the common log. Common log. When there is no base written, it's base 10. Okay? So what about this strange symbol for a logarithm, ln? Well, what ln stands for is natural log. And notice there is no base written. So natural log, just like the common log was log base 10, natural log is log base e. Remember e from the continuously compounded interest formula? It was roughly equal to 2.71 and some change, an irrational number. It's log base e. So natural log is log base e. And both in these logarithm calculations are located in your calculator in the bottom left corner area. That's where you can find them on the calculator. So 2 things to know. Common log, when there is no base 10. When it's ln with no base, that means natural log, which is equivalent to saying log base e. All right, evaluation of logarithmic expressions. What does it mean to evaluate something? Well, evaluation means to determine the value of something in the context of logarithms. So when I say evaluate log base 2 of 8, I want to know what this is equal to. And we're not really that familiar with logarithms, so our brain is not really trained to think of logarithms and just know what they are without converting it to something else. So the steps to doing this are start out by saying, okay, we want to know what this is equal to. So we're just say equals some variable, equals x. I usually use x. Then, to make it easier to think about, I convert to exponential form. So here's my base, that's 2. I swoop my 2 over, make it 2 to the x power, now equals 8. Okay, now this is easier to think about. 2 to the what equals 8? Well, we know 2 times 2 times 2 is 8. Because 2 times 2 is 4, times 2 one more time is 8. So we know x has to equal 3, because 2 to the 3rd power, if I multiply 2 by itself 3 times, that equals 8. And there we go. All right, let's try some more of these. So we have 1/4. So again, we start by thinking, okay, what is this equal to? And the best way to start is by saying equals x, or I'm going to say equals question mark, because you can also do something like that, equals question mark. We want to know what this is equal to. So we rewrite in exponential form. We bring our 4 over, make it 4 to the power of unknown, question mark, equals 1/4. Because remember, when we remove a base from a log, the log goes away. We've got 1/4 equals 4 to the what? Well, if you remember your negative exponent rules, a negative exponent flips our fraction upside down, or flips our base here. So this is actually 4 to the negative first equals 1. So we know this is equal to negative 1. Negative 1 is log base 4 of 1/4. Okay, log base 3 of 27. Log base 3 of 27. So again, same thing, we want to know what this is equal to. I'm going to go back to x this time. So we say equals x. Again, you can use any variable you want, doesn't really matter. And now we rewrite to make it easier to think about. Rewrite in exponential form. Bring our 3 over, make it 3 to the x power, because that's our base. Comes the base on the other side of the equation. Log goes away when we remove its base. 27 is the only thing left over there. So I've got 27 equals 3 to the x. Now hopefully I can think of this, okay, 3 to what power equals 27? Well, I know 3 to the second would be 3 times 3, that's 9. Times 3 one more time would give me to 27. So x would have to equal 3. Because I have to multiply by 3 times, which is 3 to the 3rd, to get to 27. So that's how we can get what this is equal to 3. All right, there are also some special cases of evaluating logarithmic expressions. So some special cases. Log base 2 of 2. All right, so let's think about what that would equal if we want to evaluate that. So we say equals x, or equals something, and we rewrite it. So take our base, bring it over here, and we say 2 to the x power equals 2, because our log went away when we took away its base. So 2 to the what equals 2? Well, we know x would equal 1. So this actually is generalizable. When I have log base something of itself, that always equals 1. So here's our good generalizable rule. Log of something of itself equals 1. So by definition, if I do log of 10, like common log of 10, that's log base 10 of 10, so that'd be equal to 1. Or natural log of e. Remember, natural log is log base e, so natural log of e would also be equal to 1 by applying this rule. Okay, log base 3 of 1. Let's investigate that one. Log base 3 of 1. So again, we want to figure out what this is equal to, so we'll say equals x or equals, we'll go with y this time. Doesn't really matter what variable, again, we use. So we rewrite it, bringing our base over here with the y. So we get 3 to the y power equals 1. Again, our log disappears when we remove its base. So 3 to the y power equals 1. 3, if you think to ourselves, 3 to what power equals 1? Well, it's 3, so it can't be like 3 to the first, that'd be 3. 3 to the second, we're going the wrong direction, that'd be 9. So remember, 3 to the 0, any number to the 0 power is equal to 1. So that would mean that this would be equal to 0. Okay, so our generalizable rule here. If I have log base something, anything, of 1, that will always equal 0, as long as a is greater than 0. So log base something of 1 will equal 0 as long as a is greater than 0. Okay, and I mean this a right here. That's what that a is. All right, last one. This is kind of a fancy one that I'm not going to show you the derivation of, but the basic idea, when I have a constant 7 raised to the power of log base 7 of 5, what happens is this cancels out. So it'll cancel out. That 7 in the log 7 part of this will cancel, leaving you with just 5. So this equals just 5. So our generalizable rule here is when you have a to the power of log base a of b, so we've got a to the raised to the power of a logarithm, and these two are the same, this will just equal b. There's our third generalizable rule for evaluation. So log base something of itself equals 1. Log base a base something of 1 will equal 0 always, as long as a is greater than 0. And then when you have a base raised to a log of the same base, then those will cancel and you'll just be left with what's left up here. All right, moving right along, checking our understanding. So I want you to pause the video and try to evaluate these without a calculator. All right, hopefully you paused your video and now you're ready to go over the answers. So we start by writing a variable. We'll just say a this time. Again, I'm just emphasizing the fact that it can be any variable we want. So we want to figure out what is the value of a, because we want to know what is log base 5 of 25. So we rewrite this in exponential form to make it easier to think about. So we identify our base, swoop it over, 5 to the a power equals 25. Remember, our log disappears when we remove its base. So I've got 25 equals 5 to the something. Well, we can start testing out numbers. It's not 5 to the 1, that'd be 5. 5 to the 2, 5 to the second power. 5 squared is 25, so a would have to be 2. So then this expression equals 2. But this is a perfectly good way to accept this. Okay, or to represent this. All right, a more difficult one, log base 2 of 1/8. Again, let's just say equals x or equals whatever, doesn't matter. We're just putting a variable there as a placeholder to help us work with rewriting it. So identify our base, that's 2. Swoop to the other side. Make it the base of an exponential expression. So 2 to the x equals, log went away, 1/8. Again, remember, when we're rewriting from a logarithm form, we can't have a log in this answer. That can somewhat be a little tricky sometimes when you're first getting used to this. All right, so this is tougher because this is not super apparent what I'd have to raise 2 to get this. But the key is noticing that's a fraction. And a fraction indicates a negative exponent. Negative exponent, that's what that means. A negative exponent, this is going to be. So if you start to think that way, you know then, 8. 8 is 2 to the third. So since if this is the same thing as 1 over 2 to the third, then x would just have to be negative 3 to turn 2 into 1/8. 2 to the negative third equals 1/8. All right, moving right along. All right, some other properties. two rules. We have a power rule and a product rule. And these are rules for logarithmic expressions. So it's not like we're working with an equation. We're just saying if we have log base b of something to a certain power, the power rule states that you can take whatever that power is and bring it out front and say it's c times the original log base b of x. Notice all we did was we took whatever the exponent of the argument was. Remember, x is the argument of the logarithm, the base and the argument. B is the base, x to the c is the argument. But if the argument has an exponent, you can swoop that out in front and make it a coefficient. This is c times log base b of x. That's what the power rule states. So and what this is called, when we change the exponent into a coefficient like that, that's called expansion. We're making the logarithm bigger, so to speak. So we're going to expand these two logarithmic expressions using the power rule. All right, so we've got this exponent here, that 5, that swoops out front. So we've got 5 times log base 4 of x. And there we go, 5 times log base 4 of x. Nothing too crazy there. Again, works the same way here. 2 swoops out front, that's the exponent. And we've got 2 times that logarithm that remained, log base 3 of a. Again, nothing too fancy here. That's the power rule. Next, you have the product rule. This one's a little more complicated. So here's the product rule. So if you have log base whatever, let's just call it log base x. Could be log base anything. Of a times b over c times d. So essentially you have things written up top, things written on the bottom. So when you go to expand this, the way you can write it is as follows. So it's going to be, notice how we have 2 up top and 2 on bottom. I'm going to rewrite those in green. So a times b, so we've got log base x of a plus log base x of b. Notice how the 2 that were in the numerator were written both positive, whereas the ones from the denominator are going to be subtracted. So we're going to say minus log base x of c minus log base x of d. So that's all we did. If it came from the numerator, it was positive, and these are just the sums and differences of all these individuals. So whatever this x was, that's the log base of all of these terms. And then if it comes from the numerator, it's positive and you add it. If it comes from the denominator, you subtract it. That's that simple. So let's use the product rule to expand this. I'm going to show this with examples, often easier to follow that way. So remember I've got 2 things inside my parentheses, 2 times x. So when I expand this, it's going to be log base 7 of 2 plus, since there is no denominator here, it's like over 1, but there is no denominator there, log base 7 of 2 plus log base 7 of x. So notice how they were both in the numerator, so they were both positive. Had there been anything underneath, we would have subtracted something, but there was nothing, so we didn't subtract it. All right, let's take a look at this one next. All right, so we've got log of c over 5a. Log of c over 5a. And again, remember there is no base, so the implied base is 10. You don't have to write the base. You can use the common log. So I've got log of c, because notice that's from the numerator. That's the only thing in the numerator. So these two I'm going to subtract. Remember, it's not log of 5a. Because remember, those are separatable. That's a 5 and an a. Those are separate. So instead, I'm going to write minus log 5 minus log a. So that is completely expanded using the product rule. All right, now we can put them together. And we can use both the power rule and the product rule at the same time to expand logarithmic expressions. So I've got log base 5 of x to the 5th, y to the 3rd. Well, first I'm just going to treat these as separate. X to the 5th times y to the 3rd. Those are 2 separate terms. So I'm going to start by using the product rule to just write them as the sum of log base 5 of x to the 5th plus log base 5, again, those two 5s came from right here, of y to the third. So notice they were both in the numerator, didn't need to subtract anything, there we go. But now, since I still have exponents here, I can now use the power rule to turn those exponents into coefficients. So they're both going to go out front like that and become 5 times the thing that would remain was log base 5 of x plus 3 times log base 5 of y. And that is our final answer for this one. All right. For this next example, we got log base 4 of 3 divided by a to the 4th times b to the 7th. Both of these in the denominator, so they'll both be negative when we go to expand initially. This is the numerator, so I'll be positive. So we start with our product rule, log base 4 of 3 minus, notice it's minus because we're from the denominator, log base 4 of a to the 4th. And remember, these 4s, this 4, those are all coming from this right here. They're all the same base, always. Okay, so we have minus log base a to the 4th minus log base 4 of b to the 7th. So we've successfully expanded using the product rule. Now we have to use the power rule to continue simplifying and continue expanding to get rid of these exponents here. So this just comes down, log base 4 of 3, minus, this 4 comes out front here, so minus 4 times log base 4 of a, minus 7, again this 7 comes out in front of that logarithm, times log base 4 of b. And there we go. So that is our fully expanded logarithmic expression. All right. Next, we've got the power rule and the product rule. We want to use the power rule and product rule to condense the logarithmic expressions now. Again, expanding is starting with essentially a condensed logarithm and making it as large as possible using the power and product rule. Here we have, it's almost like working backwards. The answer to an expand problem is the starting point to a condensed problem. And again, there's not much to condense here, but we can still do it. So I don't have multiple terms, so I can't condense using the product rule, but I can condense using the power rule. This coefficient can come back up here and just make it natural log of x cubed. And I'm done. Natural log of x cubed. And I could write it with parentheses or not. It's the same thing either way. Natural log of x cubed. Okay, next. Here, I have a bunch of terms. Some are added, some are subtracted. This is, when we have this, first we want to use the power rule. So power rule would be first. None of these have coefficients, so there is no power rule for this one. But we would want to first use the power rule for this kind of problem. So we would have, so we'd start by doing what? So we look at the positive terms. Those are going to go up top. So we've got log base 2. We know it's going to turn into, because we have positive and negatives, we know we're going to have numerator terms and denominator terms. The ones that were positive, these two, end up going on top. So we've got a times t. And then on bottom, the negative term goes there. So I've got a times t over d. And that's how we condense this expression. Now, I made a slight mistake here, so I want to rewrite this. So we're going to start. So we got 2 log x plus 3 log y minus log 2. So here's our starting point for our condensing problem. So notice how we have coefficients within our terms. We want to start by handling those coefficients. There is no coefficient for this subtracted term, so we want to handle these first by putting them back up here and making them exponents again. So I'm going to have log base x, or sorry, the common log of x squared plus the common log of y to the third. Remember, those coefficients became exponents again. And then there is no coefficient here, so we say minus log 2. All right, so now that we have no coefficients, we can now use the product rule to put them all back together. So I've got log of x squared times y cubed all over 2. Again, the ones that were positive go up top, the ones on bottom, or the ones that were subtracted, go on the bottom. And that is our condensed example. So you're going to pause and try these two problems now. So pause the video, unpause when you're ready to check your answer. All right, so for this one right here, our answer ends up being, we're expanding this one. So we've got 2 times log x. That comes from log of x squared, which then the 2 comes out front. My other term, I'm going to have log of y. That one won't change. There is no exponent there. Then I'm going to have subtracting log a. Since there's no exponent there, that one's done. And then lastly, we've got minus log of b cubed. The 3 is the exponent, so that can come out front and be minus 3 log b. And that right there, that's our final answer for that particular problem. Okay. Next, now we're condensing. We're working backwards. So when we're condensing, we want to start with the power rule. So we bring the coefficients back up there. So I've got log base 3 of x squared plus log base 2 of y to the 3rd power minus log base 2 of 7. Okay, I made a mistake here. I meant for this to be a log base 2 to match all of those. So these should all be 2's. So that should have been a 2 right there. You can only condense when all of these log bases are the same. You can't condense for different log bases. So this, we're going to pretend these were 2 the whole time. So we've got 2's all the way through, and we have, since we got rid of all our coefficients, we can now use the product rule to bring them all back together. So the positive ones, remember, go on top. We've got log base 2. Our positive ones go on top, so these two, the x squared and the y cubed. So we just say x squared y cubed. The negative one goes on bottom, it's a 7, so it's just over 7. And that's our final answer.